VI characteristics of a diode, that is voltage ampere characteristics of a diode, voltage current characteristics. When a diode is in forward biased condition, that is positive terminal of the battery is connected to the anode and negative terminal of the battery is connected to the cathode. In this condition, if the applied voltage by a battery Vf is less than V gamma, that is cut-in voltage of the diode, then diode will not conduct and the current flowing through the diode in this condition, that is Vf is less than V gamma, there is a small current flowing through this diode. Practically, the current is assumed to be zero. The diode will have a cut-in voltage or threshold voltage, that is V gamma. Here you can see. And below that voltage, the diode do not provide any current. For different materials, V gamma will be different. For germanium, it will be 0.2. For silicon, it will be 0.6 volts. As forward biased voltage Vf, that is, or applied Vf, that is battery voltage, is greater than this V gamma. In this condition, Vf is greater than the cut-in voltage V gamma. V gamma is the PN junction diode voltage. The potential barrier across the junction is completely eliminated and the current rises very rapidly. That is, Vf is greater than the potential at battery is greater than the potential of PN junction diode, potential barrier of PN junction diode. Then this potential barrier present in this PN junction is completely eliminated and it leads to current flow in this manner. So due to the rapid rise in current, it will lead to current flow. Based on the applied potential for germanium at 0.2, the cut-in voltage gets crossed so that germanium allows current flows through it. Similarly, silicon also from 0.2, the cut-in voltage of PN junction. So from 0.6, the potential barrier gets eliminated and it allows the current flowing through it. Now, if you consider the reverse biased condition, what is the reverse biased condition? Anode of PN junction is connected to the negative terminal of the battery. Cathode of PN junction is connected to the positive terminal of the battery, where VR is the reverse bias voltage given by the battery. Now, when a PN junction is in reverse bias, the negative terminal attracts the holes in this p-type material and positive terminal of the battery attracts the electrons in this n-type region of PN junction diode. So no current or no charge carriers will cross the junction actually. The electrons and holes both move away from the junction. In the depletion region widens. Both holes from p side and electrons from n side are moved towards the battery. That's why the depletion region gets widened. As depletion region widens, potential barrier across the junction increases. As same as that of applied voltage. Since the polarity of the potential barrier are same as that of applied voltage. However, a small reverse current is called reverse saturation current I0 flow across the junction due to movement of minority charge carriers across the junction. In n-type region, I have minority charge carriers like holes, and in p-type region I have minority charge carriers like electrons. The electrons in this p-type region will move towards this n-type region, and the holes in this n-type region of the diode will move towards p-type region. Due to that, a small reverse saturation current IR will be generated. Reverse saturation current will be microamps for germanium, small few microamps for germanium, and for silicon it will be few nanoamps. The generation of minority charge carriers depends on the temperature and do not depend on the reverse biased voltage. That is, it does not depend on the supplying voltage by the battery. The reverse biased current depends only on the temperature. If the reverse biased voltage is increased beyond certain limit, the junction breakdown happens and very large reverse current flows. That is, if we increase this battery voltage, then what happens? Battery voltage or reverse bias voltage, what happens? The the holes present in the p-type region will attract very fastly, and the electrons present in the n-type region will attract fastly towards this positive terminal. This leads to what? A rapid, high and heavy generation of current. And leads to breakdown. The VI characteristics under reverse bias of a PN junction will be look like this. Mainly in reverse bias, the current conduction will be due to thermal energy. Due to thermal energy, the covalent bonds present in this PN junction diode will acquire the energy required to become free electrons and create free holes. Due to that free electrons and free holes, the conduction mainly happens, that is called avalanche current. Even at some potential, this diode acts as a Zener diode, and if you increase much more potential than the Zener diode potential, it acts as avalanche breakdown. This is the reverse saturation current. Basically, it also contains like this. At this potential, at this voltage, the Zener breakdown happens, and if we apply the much more potential at a time in reverse bias, then avalanche breakdown also happens. If we see the overall EI characteristics in forward bias as well as reverse bias, it will be like this for germanium as well as silicon. This is a reverse breakdown of these diodes